All right, so now we're going to take a look at one concept. We're going to introduce it now, and we're going to use it a lot for the rest of the semester. And probably if you take other chemistry classes, you will see this very frequently. And that's the idea of the mole. And we'll come back to the definition here in a second, but just to give you a sort of a background of why this is important, we just spent a whole lot of time talking about the fact that the matter around us is made up of these really tiny particles called atoms. So small we can't really see them with our naked eyes, but we still see the stuff that atoms make up, right? So the pen that you're using to write, or the salt that you add to your food, or the sugar that you add to your drinks, right? All of those are made up of atoms. We can't see individual atoms, but we can see when there are huge numbers of those atoms and molecules, etc., to things that we can touch. So the mole then is going to be our bridge between the realm of the really tiny, the microscopic, and the realm of our regular everyday experience, things that we can touch and feel and see with our eyes. Right, so the mole is going to be the bridge between the really tiny and the microscopic world. So we have these tiny things. We need a lot of them, okay, to make up the amounts that we actually see or that we can measure. And the mole is going to allow us to do that. So when we talk about the mole, we define it as, as the amount of something, of a substance that contains as many things in that substance as there are atoms in 12 grams of the isotope of carbon-12, right? So that's a long-winded definition. In terms of how this is useful to us, when we have a mole of something, 1 mole of anything, whatever that thing is, it always is going to contain a certain number of that thing. And that number is called Avogadro's number. Avogadro's number is abbreviated N, capital N, subscript uppercase A. And it's named after a scientist, Amedeo Avogadro. That number itself has a value, and that value is, we'll round it typically to 3 decimal places, 6.022 times 10 to the 23 of something, right? So again, you're looking at this number, positive exponent, pretty big number, right? And if you think about it, it kind of makes sense. If you have, really tiny things like atoms, you're going to need a lot of them to make up the amounts you can see that you can measure out. So we can come up with a relationship or an equality to help relate now these two terms. So 1 mole of anything is equal to 6.022 times 10 to the 23 of that thing, right? 1 mole of anything, whether it's a mole of cookies, you have that many cookies. If you have a mole of elephants, you have that many elephants. If you have a mole of hydrogen atoms, these are how many hydrogen atoms you have. And by the way, mole is often abbreviated as MOL. So not much of an abbreviation, but it's used a lot. So just keep that in mind. So you think about it, the mole is really just a counting measure that we use. Just like if you have a dozen of something, that means you always have 12 of that thing. You have a pair of shoes, you have 2 shoes. If you have a mole of shoes, right, you have this many shoes, right? So when we work in the laboratory and we measure things out, it's very difficult to count these many, atoms or molecules. It's a lot easier to measure out number of moles, and we'll see the relationship here in a second. Okay, so 1 mole of anything is equal to 6.022 times 10 to the 23 of that thing. So we can take that relationship, this equality, And we can manipulate it just like we did every single other equality we saw before, whether it was a metric equality or an equality that related a metric unit to a different unit or different system. It doesn't really matter, right? And this is why the dimensional analysis technique is so powerful. We can apply it to this exact scenario as well. So if I have 1 mole equals Avogadro's number, I can put them over each other. And I can flip it to get the other conversion factor. Okay, so this is no different than the technique we used when we converted centimeters to meters or whatever, except now we're looking at moles. Okay, but the technique is the same. So let's take a look at a specific example. Let's say that we're told that calcium, a typical human body, contains 30 moles of calcium. Determine the number of calcium atoms in that sample. Okay, so we want to organize the information. So we're given here 30 moles of Ca. What we want to get to is the number of Ca atoms, number of calcium atoms. And what we're going to use now is the mole and Avogadro's relationship. To get from the moles to the atoms. So we can say then that relationship, and it's always the same relationship, 1 mole of something, in this case it's calcium atoms, so keep track of the units, just like we've done previously, is equal to Avogadro's number, 6.022 times 10 to the 23 calcium atoms. Okay, that's my equality. Same equality I saw before. The only thing now that I did differently is I inserted the actual unit, calcium atoms and calcium atoms, into it. So if I start with what's given, the 30 moles of Ca atoms, calcium atoms, put that over 1. Then I can take my equality, I can insert it in here. If I want to cancel out the moles of calcium, I'm going to put that on the bottom. Okay, so they're diagonal to each other. And then the unit that I want goes on top. So my 6.022 times 10 to the 23 calcium atoms. Get moles of calcium go away, and I end up with just a number of calcium atoms. So I evaluate that my calculator, so I end up with we needed 30.00, right? So let's pay attention to the sig figs. So I have 4 sig figs in this first number, and then my Avogadro's here, I use 4 sig figs, so my final answer should have 4 sig figs, so this would be 1.807 times 10 to the 25 calcium atoms. Okay, so we have a number here. The units make sense because everything else canceled away. Now let's take a look at the actual value, right? So you get an answer. Before you celebrate too quick, let's think about the answer. So does that answer make sense in terms of the magnitude of it? Okay, we said before a mole of something is a huge number of that thing, right? 10 to the 23. So if we have 30 moles of something, we should also have a fairly big number, right? So our exponent here should be positive, and it is. So it makes sense in terms of the magnitude, and then it makes sense in terms of the sig fig rules that we apply. So you always want to make sure that you check your answer. Does it make sense from those 2 perspectives in terms of the units, which tells you set it up correctly, and the magnitude of the answer? Does it make sense in terms of roughly, should the number be big? Should it be small? So Avogadro's number and the mole can be used to convert between moles of something or moles of, in this case, we're looking at atoms, between moles of atoms and number of atoms, right? So we can go back and forth between moles and number of atoms, depending on what we're given and then what we need to find. Now, when you start working in the laboratory, right, you'll see that when you measure things out, for example, calcium, let's say, there is no measuring device for counting, at least in our lab. There's nothing that allows us to count the number of atoms, so we wouldn't be able to determine the number of moles that way. And there definitely isn't a device, a measuring device that tells you directly you have this number of moles of something, right? So if you're trying to measure out, a certain number of moles of, I don't know, let's say iron in the lab, it's very difficult for us to count the number of atoms, of iron atoms to get to moles. It's very difficult for us to actually measure moles explicitly. What we can do, though, is we can easily measure the masses of things in the laboratory. And there is a relationship now between moles and mass that we can use. And that relationship is called the molar mass of the elements. So generally, we can say the molar mass of anything, of a substance, is the mass in grams of 1 mole of that thing, of that substance. We define the mass of a mole of carbon-12, for instance, as exactly 12 grams. And as we saw before, when we looked at atomic masses, we saw that the mass of one carbon atom was exactly 12 atomic mass units. Now we're saying that the mass of 1 mole of carbon-12 is exactly 12 grams. So if I take a look now at the molar masses of our elements, what I can use is simply the periodic table to determine these. Okay, so let's pick, for instance, iron, which has the symbol Fe. Okay, so there's my periodic table. I'm going to find iron in it. Let's see, iron is right there in the middle. Okay, so it is part of the transition metals. So there's Fe. And if I zoom in, okay, we said that in the periodic table entry, we have the atomic number on top, and then this number underneath, that is the atomic mass. That's the weighted average mass of, considering all of the naturally occurring isotopes of iron together with their percent abundance. So that tells me that one iron atom then would have a mass, an average mass of 55.845 atomic mass units, right? You get that directly from the periodic table. There is nothing to think about. You just look it up on the table. Now, what we're saying in terms of the molar masses, okay, if I have 1 mole now of iron atoms, I mean, iron is Fe, I'm not looking at just one iron atom now. I'm looking at 1 mole of iron atoms. So this would be 6.022 times 10 to the 23 iron atoms. What we find is that the 1 mole of Fe atoms is actually equal to 55.845, not AMU now, because that would be the mass of just one iron atom, but 55.845 grams of iron. And this is the molar mass, the mass of 1 mole of Fe. And where do I get that from? I get it from the periodic table, right? Again, something I do not need to calculate. As long as I have a periodic table, I can look this up for every single one of the elements. I know what the molar mass is. So the molar mass is simply that same number that you see on the periodic table, but now the unit is grams as opposed to AMU, right? And that's the case for every single one of these elements. So because the molar mass relates moles to grams, we can use the molar mass to convert between moles and grams of something, of elements, for instance. And the way that that we represent the molar mass. So we can say, we can represent it a couple different ways. One way is maybe a little bit more user-friendly than the other. So we see the molar mass of Fe is equal to 55.845 grams per mole. Okay, so grams per mole would be the unit for molar mass, or sometimes you'll see 55.845 grams times moles to the -1. Again, it means the exact same thing. What's even more useful to us is to express the molar mass in an equality form, right? Just like we did before. So 1 mole of Fe is equal to 55.845 grams of Fe. And it means the same thing as the grams per mole. The reason why I want to stress this way is because in an equality, right, I can turn it into my two conversion factors. So 1 mole of Fe over 55.845 grams, and I can flip it, 55.845 grams of Fe for every 1 mole of Fe of iron. Okay, so it relates, the molar mass relates moles to grams, which means we can use it to convert between those two units. So we use the molar mass to convert between grams and moles of something. Sometimes you will see molar mass being abbreviated a couple different ways, depending on your textbook and other places. Molar mass is sometimes abbreviated as MM, big M, or you see with a stylized M like this. So that's what it means. It means the molar mass of whatever comes after it. So let's take a look at an example, and we'll do, let's say, well, we'll just use iron because we have it here already. So let's say that we measured out 35.45 grams of iron was measured out. What is how many moles of iron are present? Okay, so here again, what we're given the 35.45 grams of Fe. We want to convert this to moles of Fe. Okay, so we're going to use the molar mass, which we know what that is now. Look it up on the periodic table. So 1 mole of Fe is 55.845 grams. So when I set this up, again, units are going to guide you, which is why I would encourage you when you set these up, don't just put the number, put the units in as well. All right, so if I want to end up with moles, right, I put the unit that I want on top. So for every 1 mole of Fe, I have 55.845 grams of Fe. Grams go away. I end up with moles of Fe. And if I evaluate that with my calculator, right, you should get a number that would be smaller than 1, because if 1 mole is 55.845 grams and you measured out 35 grams, that's less than a mole, right? So 35.45 divided by 55.845, and that gives so we need to have 4 sig figs because that's our initial value. The other one has 5 sig figs, so 0.6348 moles of Fe in that sample. So the number makes sense, the answer makes sense, both in terms of the unit, makes sense in terms of the magnitude of the number as well. So we can do this in the opposite direction as well. If we're given moles, we can convert that to grams of the substance, of the element. Let's say, we'll do one more example. let's say that we're given, or that we measured out 0.321 grams of carbon is measured out. And then we're asked how many carbon atoms are present in the sample. Okay, so now we're given the mass so we have 0.321 grams of C. We want to convert this eventually to number of carbon atoms. Okay, so can we do that in one step? Was there a relationship that we talked about that related grams to number of things? Well, we didn't. We talked about the relationship between number of something and moles of something, in this case, moles of carbon atoms. And then we talked about the relationship between moles of something and grams of something. So then it would make sense if I wanted to go from grams to number of carbon atoms, I'm going to go through the number of moles. So I'm going to convert the grams to moles first, and then I can convert the moles to the number of carbon atoms. So what am I using in each of these steps? Well, to go from grams to moles, or moles to grams, I'm going to use the molar mass, in this case of carbon. So that's, we look it up on the table, 1 mole of C is 12.01 grams of carbon. That's my quality, molar mass. And then from moles to number of things, right, that's Avogadro. So use Avogadro's number. So 1 mole, in this case of carbon atoms, is Avogadro number of carbon atoms. So that's my quality there as well. So I'm going to set this up. I start with what's given, 0.321 grams of C, put that over 1. I'm going to take my equality, insert it here. The units are telling me where to put them. So if I want to cancel out grams, that goes on the bottom, along with the number, 12.01, which means the moles of carbon go on top. That's what I want, because my middle step here is to get to moles of C. Grams of C goes away. And the next step, I want to end up with number of carbon atoms, and I want to cancel out the moles, right? So moles then is going to go on the bottom. Every 1 mole of C, I have Avogadro's number, 6.022 times 10 to the 23 carbon atoms. Moles go away, and now the only unit I'm left with is carbon atoms, and I just need to evaluate this using my calculator. So I have, if I enter that in, so 0.321, and I divide that by 12.01. Okay, so that's going to give me, let's see here, we have 3 sig figs, 4 sig figs, 4 sig figs. So my final answer should have 3 sig figs, and that was 1.61 times 10 to the 22 carbon atoms. Okay, so the answer makes sense in terms of the unit. Doesn't make sense in terms of the magnitude, right? We're trying to calculate here the number of carbon atoms in a sample. So again, atoms are really tiny. You're going to have a lot of them, even in the smallest sample possible. So yes, the magnitude here makes perfect sense. I have a huge number. Even so, it's less than Avogadro's number because 1 mole of something of carbon is 12 grams, and I have way less than a mole, right? So 0.321 grams. So the number here is less than Avogadro. So that makes sense as well. So as you go through your calculations, and again, the only way to get better at these is to practice, practice, practice. You want to use the relationships just like we did with the dimensional analysis early on. So to get from grams to moles, we use the molar mass. To get from moles to atoms, we use Avogadro's number. And if we wanted to go from grams to atoms or from atoms to grams, we have to go through the moles in the middle.